Oh, okay. Nah, it's all right. It's just, you know. Yeah, yesterday we had a slow span of a few hours. It was really slow. Sure. Yeah, it was. It was on their end, and they admitted it too. They're like, "Yeah, that's our servers or whatever." It was yesterday. It was just, yeah. So, any questions? How's yes? Oh yeah, that's a good question. Let me see. I will start with chapter two. Yeah, yeah, I know, doesn't it? We're losing people. But yeah, we'll probably start in chapter. Don't tell the other section. Remember the deal? Don't tell the other group. Ah. So, okay, other questions? No questions? All right, well, we're still in chapter one. Chapter one, again, it's mostly familiar material. We will introduce a notion of a function today. So, some of you already know what a function is. Well, let's just do that really fast. So, for that section, probably 1.2 functions. And then there's going to be about 2 or 3 sections in chapter one talking about equation, the line, and the slope, and all that stuff. And we're kind of going to cover that simultaneously. So, yes, functions. So first, we will define an idea that's called a relation. And basically, the relation is a set of ordered pairs. So if you see something that can be described as a set of ordered pairs, then you got yourself a relation. So no restrictions. So example would be something like this, R equals, so then I can just list something like that. So since this is just a set of ordered pairs, that means I got myself a relation. There's no other conditions. Now, what it means, when you see an ordered pair, let's say 1 comma 0, that really means that 1 relates to 0. That's all I know. Why it relates to 0, I don't know why. All it says that it relates to 0. Now, it doesn't work the other way. If 1 relates to 0, it does not mean that 0 relates to 1. That is just a little weird thing. In order for me to say, let's say here, -1 relates to 2, in order for me to say that 2 relates to -1, I do need to see an ordered pair like that to say that 2 relates to -1. Like a more concrete example of a relation, we can say that, for example, one number relates to another number if the first number divides the second number. Relation of divides. So 3 relates to 6 because 3 divides 6. Or 5 relates to, I don't know, 15, right? But it doesn't work the other way. 15 does not relate to 5 under that relation. Does that make sense? I mean, don't worry about it. It's not that crucial. Now, the set of all x values, the set of all inputs, the first places in each ordered pair is called a domain. So domain, in this case, would be just the first numbers. So 1, -1, 3, 2. I don't need to list 1 again. So domain are the inputs, all the x values. And the range would be all the outputs, all the y values, which are, what is it, 0, 2, 1, 4, -1. I don't have to list them in order. I can if I want to, but I don't have to. Now, so yeah, so that's what a relation is. Now a function is a relation so function is a relation so that for every x in the domain, sorry for blocking it, there is a unique y in the range. Now what this means is that same x value cannot relate to two different y values. Okay, that's what it's saying. So an example, so like here you see the two ordered pairs, so 1, 0, and 1, 4. You have same x value relating to two different y values, so this particular relation is not a function. Okay, we don't want to see that repetition in the x. Now, example of that would be if I can come up with a function of students taking classes, and when you're working on your schedule, you probably don't have a class scheduled from 1 to 2:50 on Mondays, Wednesdays, besides this class, right? How many classes are you taking right now? 8, but in this time slot? 1, right? So you cannot be in 2 classes at the same time. Now, can many of you be in the same class? Yeah. So it is okay to have different x's relating to the same y value, but it's not okay to have same x relating to 2 different y values. Okay? So another way to say this phrase, no repetition in the x. Now, so for example, let's f equal to 1, 0, 2, 0, 3, 0, 4, 1. Is f a relation? Yes, just set of ordered pairs. Is f a function? Yes, because there's no repetition in the x. That's all we worry about. All x values are different, right? If some of the y values are the same, that's okay. What is the domain of f? I'm going to write like this. 1, 2, 3, 4. What is the range of f? 0, 1. Right? It's 4, 1, close parenthesis. But you can make it whatever you like. Doesn't matter. We'll just change the range here. Is that okay? Make sense? Now, all right, good. So that's kind of an idea of a function we'll be doing. Mostly with functions, they're easier to play with. So 1x gets a unique y. Function notation, most of you are familiar with. We write something like that. That equals to algebraic expression in terms of x. And the way you pronounce this left side, it's pronounced as f of x. So this is how you say that. It's not a product, it's just a notation. Now this whole f part, that's the name of the function. X indicates the independent variable. So if I write something like this, and I say this is some version of a function notation, what is the name of that function? Yeah, it's kr of t. It's whatever the kr function does, t is the variable. That's just, again, doesn't have to be one letter, doesn't have to be a word, could be a symbol, it could be some Greek letters. That's still acceptable. Name of the function followed by the independent variable. There's no operation in here, there's just a notation. Okay. So let's do an example. Let's say we have, the way this function notation works, f of x, let's say it equals to x squared plus 2x plus 1. Okay? So whatever you feed to that function, it will get squared, it will get doubled, and then 1 will get added to the whole thing. Okay, so what it means, if I ask you to evaluate f of 2, that tells you that the value of the variable right now is 2. So 2 goes in and replaces every x in that function, so it's 2 squared plus 2 times 2 plus 1. See what happened? Are you okay with that? Right? You've probably seen this before. What does that equal to? 9. Yeah? How about f of negative 3? What would you do with that? Yeah. So every x is replaced with negative 3, so it becomes negative 3 squared plus 2 times negative 3 plus 1. And then we'll compute that, right? So what would that be? Maybe. Yeah, 9 minus 6 plus 1 equals 4. Yes, you're way ahead of me. Good. Does that make sense? How that operates? Yeah? What if I ask you this? F of t. What would f of t be? T squared plus 2t plus 1. Right? What if I ask you f of that? Right. I just need to get creative with putting smileys in there. Here we go. Well, I can do that, right? That'd be a set. No, I always do a smiley face. But the idea is whatever lands in this parenthesis replaces the variable. So if I ask you what is f of a plus 3, what would you say? What? No more square plus 1, right? So a plus 3 quantity square plus 2 times a plus 3 plus 1. So again, replaces the variable. This is a, by the way. That looks like a 9. Can we expand that? How do you square a plus 3? Foil it. So you can either write it as a plus 3 times a plus 3 and foil. Some of you might know a quick way of squaring a plus 3. Who knows a quick way? Right, that's the FOIL, right? Yeah. But there's a special formula that allows you to square a sum. That'll just give you the answer. By the way, the worst thing you can do is to tell me it's a squared plus 9. That makes me upset, and I will pass it on. I will not hesitate to hurt your feelings in return if you write something like that. Oh, yeah. So, right? But you can FOIL, that's fine. You know, a plus 3 times a plus 3, FOIL this. Or some of you might know the formula, and I expect that you know the formula, especially since we proved this formula with drawing squares and rectangles the other day. Remember that? This formula will allow us to square a plus 3 fast. So it tells me to go a squared plus multiply these two things and then double it. That's what that 2 does. So 3 doubles becomes 6a plus 3 squared, which is a 9. You get the same result by FOILing, and you know, please FOIL if that's your thing. Then distribute 2, and then plus 1. Combine like terms gives me a squared plus 8a plus 16. Yeah. Is that okay? Good. Okay, so let's play more with domain and range. So again, remember, the domain is whatever your independent variable can be. Okay? So nothing bad happens. You have 2 things that can go wrong with your function right now. We'll add extra dangerous areas as we move forward, but there are 2 things you should be looking out for. One is division by 0, right? Because that's frowned upon. Agree with that? We don't want to be dividing by 0. Taking square roots of negative numbers. Or actually taking even roots of negative numbers. That gets a little sneaky. The output is no longer real number. So what we want the input to be real, the output to be real. So if something falls in and comes out weird, that thing should not be in the domain. Okay? So division by 0, even radicals of negative numbers. Oh, that's a fancy way to say that. All right. Another way to think of this, domain is everything x can be. The range is everything that f of x can be. X is domain, f of x is range. Okay? I can actually give you a picture. I can give you a drawing of sorts. Something like that. First of all, is this a relation? Yeah, it's a set of ordered pairs. Is this relation a function? How do you know that? How do you know whether a graph represents a function? Does anybody remember from? Well, there are multiple points, but let me give you another example. Is that a relation, that second thing? Yeah, it's a set of ordered pairs. Is that relation a function? No. Yes, no? Probably. Now, what separates a function from just a general relation? What you do not want to see with functions. And by horizontal, you meant, yes. That's very good. That's okay. I mixed those up too. But yeah, you don't want to see the same x value corresponding to different y values. Well, here, you know, if I pick this x value right here, I have 3 ordered pairs that have same x value and different y values, right? So this is what we call a vertical line test. If you put a vertical line through a graph, and if that line, if any of those lines intersect your graph at more than one point, it's not a function. Okay? Probably. Let me see if I can make it more official. So if every vertical line intersects a graph in at most one point, So at most 1 point. Could miss the graph altogether, but if it hits the graph at most 1 point, then you got yourself a function. And the graph is a graph of a function. Does that make sense? Vertical line test. We'll have a horizontal line test, but a little later. So vertical line test allows us to differentiate between graph of a function and graph of whatever. So like circles would not be functions because they failed the vertical line test and so forth. But going back to this example, just by looking at the graph, can you tell me the domain of this function? And again, domain would be all x values used to produce this graph. Yeah, from -2, including -2, to infinity. So everything from here on is covered on the x-axis. Right, there's nothing before -2. Yeah.
Did you use the bracket to show that it doesn't really cover that?
Right, well, I use a bracket to show that actually -2 is a part of this domain. If I had a parenthesis, I'll probably have like an empty circle here to show that it, gets to -2, but doesn't quite get to -2. That's right. I can also say, or it's a set of all x's such that x is greater than or equal to -2. Yes, that's acceptable. And by the way, I don't have to write in x just because it's an x-axis. I can just say whatever, b such that b is greater than or equal to -2. Because it just builds a set of numbers, so whatever this dummy variable. But yeah, you use x, that's more reasonable. You don't have to. What about the range of this function? So now I'm looking at the possible outputs. I'm looking at the possible y values. What is the range here? Yeah, from 0 to infinity. The lowest y value we have is 0, and then it keeps growing, right? So you're just looking at the y-axis. So the range here would be from 0 to infinity, or the set of all x's, such as x is greater than or equal to 0. And again, you see I'm using x, although I'm describing the y-axis, but that's okay, because it just builds a set. Probably be a little politically correct if I used y, but it's not an issue. Okay? Does that make sense? How you can determine the both by looking at the graph? Think about if you're still a little slightly confused, and this will not help, but maybe think about shining a light at the graph and the shadow casted by the curve, right? Whatever's, the shadow on the x-axis is your domain, the shadow on the y-axis is your range. Like that? Yeah. Another thing, you can find a domain of a function if I just write a function without looking at the graph. You can do that. We can find domain analytically. The range is tricky. We will have very hard time finding the range of a function without seeing the graph. Okay? Later in chapter 4, or maybe even 5, in chapter 5, we'll find a sneaky way to find the range without seeing a graph. But for now, most of your problems would be, here's the graph, find the range, or here's just a definition of a function without the graph. Then find the domain. You're rarely going to be asked to find the range without graphing. They might give you an obvious function that's easy to graph, and then you can find the range. So finding the range without graph is hard. Okay? Does that make sense? Because again, most likely, the graph that we just played with is given by this function. How I know that? That's irrelevant. Let's say here's the function. We don't see the graph. Can we find the domain of this function? And you'll say, well, okay, so let's see. Square root can cause problems, right? What I need to avoid when playing with square roots? What? Well, did you hear the question? Well, what do I need to, do I have to be careful when playing with square roots? Well, I don't, it's okay not to get a perfect square, but yeah, but what? Well, I can use a negative number like -1, but I have to be careful, right? You're right. Your radicand, that's what this is, should be non-negative, right? So you have to make sure that x plus 2 does not turn negative, right? Which means you have to make sure that x plus 2 stays greater than or equal to 0. So I can actually take the radicand, and that's what you're going to do every time when dealing with square roots. You're going to take the radicand, ignore everything else, and you'll set it to greater than or equal to 0. And that's a simple inequality to solve, right? By the way, you know how to solve inequalities? We haven't talked about it, but I assume you're okay with this, right? Subtracting 2 from both sides. X is greater than or equal to -2. Bam. So that's the domain. Yeah. You just take the radicand, greater than or equal to 0, and then solve. I mean, you can now get all fancy with your notation, but that's the idea. You take the radicand, greater than or equal to 0, solve for whatever your variable is. But if I ask you what is the range of this thing, that's tricky. That's tricky to predict all possible values of y. I mean, you can think about this, well, what do we know about the square roots? Square roots will never produce a negative result, so definitely all the answers are positive. What is the smallest number that we can get? Well, if x is -2, we get 0. And then maybe you can say, well, it's from 0 to infinity. But this is a weird way to think about this. I'm still visualizing the graph. That's what I'm doing. So range is hard to answer. Well, how about this fun example? Let's say this is 2, and let's say this is 1, and then I have a weird looking graph like this. I'll say this intercept is 3. We'll study graphs like that in chapter 4. But if I just give you this graph, those dotted lines meaning, your actual graph gets really close to those lines but does not touch them. Okay? Have you seen those things before? What are they called? Real good. Yeah, but we'll study them in chapter 4 in greater details. It's okay if you don't know what those are. We're not learning that. But can you tell me the domain of this function? Just by looking at the graph. Sure. So you can say this, from -infinity to 2, not including 2, and from 2 on. Do I need both of this? Yeah. How do you glue them together? What is this? What? Glue? No. What glue you use for sets? I'm miming it very hard. Look at that. Yeah, the union. Yeah, that's what. So that's how you connect, because that'll show that I need both of them together. So you take the union. Or you can just say all x is such that x does not equal to 2. That's also okay. All right? What about the range of this function? What about the range? What are the possible y values on this function? Yeah, so y does not equal 1. Everything else is covered. So you can say y such that y does not equal 1. Again, no reason to use y, but that's okay. Or you can use the integral notation from -infinity to 1, union from 1 to infinity. Is that okay? Just by looking at the graphs. That's all we're doing. We're not solving anything, just looking at the graph, see what's covered. Now, if I tell you, consider this function, that is can you find the domain of the function that I just wrote? What do you have to be careful about? Dividing by 0. So what value of x you need to avoid? 2. But everything else will work. No other number will turn the denominator into 0. So all real numbers but 2 will work. So, you get the domain. But if I ask you what is the range of this function, without seeing the graph, it's hard to say that it's everything but 1. So that's, again, driving the point. You can always find the domain. The range, you will need a graph. Okay? Who is with me on this? All right, about half of you. That's good. Okay, let's try a few more examples, just finding the domain. So find the domain. How about this one? F of x equals x squared. What is the domain of that function? What? Just little friendly little x squared. What's the domain of that? All real numbers. Because you're looking for trouble areas, square roots, division. None of them appear. You can square any number that you like. So domain here would be all real numbers. Most of you know the graph of that function, right? So we can actually predict the range. It's just going to be all positive numbers and 0. It's never negative. So we can, we know the graph of this. So the range is also easy to find here. But again, I need to kind of think about the graph. All right, so that was simple. Any questions on this? So again, if you see a function that does not have even roots, so square root, 4th root, 18th root, or does not have a division, we're good to go. It's all real numbers. For now, we'll be adding trouble areas later on, but for now, just 2. Square roots, division. Okay? All right. How about this example? Let's say g of x equals x plus 1 over x squared minus 4. Right. Is that it? Is there any other numbers that might make your denominator 0? Negative 2. So x cannot equal positive 2 or negative 2 because of the square. Because we can actually factor that denominator. And this what we'll be doing again later and a lot when you see a function like this. It's always a good idea to factor it first. It makes it easier to play with. So now we can see that x equals 2 and x equals negative 2 would both cause trouble. Everything else will work. So the domain here would be all reals except for plus or minus 2. And this is my equal sign crossed out type of thing. It's not equal. Or if you like the interval notation, you can say it's from negative infinity to negative 2, union from negative 2 to 2, union from 2 to infinity. It's an entire number line with 2 numbers removed, negative 2 and a positive 2. Hmm? Like this? Or, so like, yeah, that's fine. That's really specific. So yeah, that's okay. I usually, if you don't say that it does not belong to real numbers, we assume that. But if you want to say they're all integers, then you kind of have to do that. But yeah, that's perfectly fine. But again, if I ask you what is the range of this function, things will get a little weird. Okay? Can you see the range? Say no, you don't see the range. It's hard. Okay? That's what I've been trying to drive at. If I don't give you a graph, you cannot predict. I mean, you can by plugging a few points. But if I grab this function for you, and the graph of this function will be It'll be hard. It'll be something like this, and then something like that, and then something like that. What is the range if this is a graph? Yeah, all real numbers, because that squiggly thing in the middle, it just covers everything, right? Those tails don't matter anymore, right? This thing already covered all real numbers, right? So, yeah. So the range here is all real numbers. Did I lie to you before? I might have. I do tend to lie. No, I didn't. Okay, good. No worry. It wasn't lying. Okay? Any questions on the whole domain thingy? What are you looking for? What are the two areas that you have to be careful with? Dividing by 0. Right. Or just any even root, right? Square for it. So if I, like we did a problem earlier today, but if I give you this example, f of x is the square root of 2x plus 5. So you see even root, danger. What do you need to do to make it work? What did we do last time? What did we do with that radicand? Yeah, so you set it to greater than or equal to 0. You want to make sure that 2x plus 5 stays greater than or equal to 0. Right? You take that and you solve this. Now, this is easy to solve. Subtract 5, 2x is greater than or equal to negative 5. And then x is greater than or equal to negative 5 halves. Right? So as long as x is greater than or equal to negative 5 halves, this function works well. So I can make my answer like that, and I'm good. That's the domain. So you with me on the process? You take the radicand, greater than or equal to 0, solve. What if this was 12th root? How would that change our answer? It wouldn't change the answer. You would do the same thing. You just have to make sure that the radicand is not negative. So you're still going to take your radicand and solve for greater than or equal to 0. It doesn't matter what the power on the top is. You just want to make it positive. If this power was 121, how would that change our answer? Or would it? What? Well, what kind of a radical is this? Is this an even radical or an odd radical? Odd. It's 121, right? Well, can you take odd radicals of negative numbers? Can you do like a cube root of negative 8? Is this pretty? Yeah, it's pretty, right? It's negative 2. So we can take odd radicals of positive and negative numbers. So in this case, the domain would just be all real numbers. I can take 121st root of any real number. Positive, positive, negative, negative, 0, 0. With even ones, I have to be careful. So does that make sense? Okay. But again, with the even ones, it doesn't matter how crazy the even radical is. You're still going to take whatever's underneath, set it to greater than or equal to 0, and then solve. Right? Yeah. Well, let's try this again. This is fun. Are you having fun? I bet you do. Well, let me mess with you now. What if I give you this? 2x plus 1 over the square root of x minus 1. Well, how many trouble areas do we see? 2. We have to make sure the denominator is not 0 to begin with, right? So x cannot equal 1. Right, I don't have to do any special solving. But here's the sneaky thing. If we didn't have the numerator, if we just had the square root, we would say, well, x minus 1 is greater than or equal to 0. Right? That's how you make square root happy. Do you agree with that? This just makes the square root happy. But equal to 0 will make the fraction sad. Right? So instead of going greater than or equal to 0, I can just go strictly greater than 0. And then it will satisfy the fact that the denominator does not turn into 0 and the square root happy. Does that make sense? Because I'm kind of killing 2 birds with whatever, 1 stone type of deal, right? Because look, if we just had the square root, the solution would be x is greater than or equal to 1. But x cannot equal 1 in this case because it will turn the denominator into 0. So you're kind of keeping track of that. Did that make sense? Well, let's try this example then. Well, what if I shove the square root in the numerator and the denominator is like that? Right, so the numerator on the top, so first I have to make the numerator happy, right? So that's what makes numerator happy. So x is greater than or equal to -2. Right, from the denominator, we know that x cannot equal to 3. Agree with that? Well, now I have to combine the both things. So basically, is 3 part of this set, the first set? Is 3 greater than -2? So it has to be taken out. So really the domain is here is everything from -2 to 3, not including 3 union from 3 to infinity. So we're kind of dropping 3 out of the whatever's left. How's this? Yeah, you liking that? Yeah. All right. Another way to express the solution, you can literally write this. It's all x's such that x is greater than or equal to -2 and x is not equal to 3. That's perfectly acceptable. And means intersection, so this is the intersection of those 2 sets. Everything that's greater than or equal to -2, but not 3. Good? Fun stuff. Who's with me on this? 3, 4, 5, 6. Okay. All right, good. All right. Okay. So, well, let me give you a problem for you to think about. F of x equals x over, oh, that's too mean. It's all right. Welcome. There we go. Oh, that's lovely. Think about this one. What you have for me? What? That's food for your, food for thought. X cannot equal 4. I like that, right? Can x equal 4? Well, you just said that, right. So, yes, you cannot equal 4. Very good. Yeah. I didn't even check. I went based on the confidence. But because what happens when x equals 4? The denominator becomes 0 when you plug in 4 in for x, 4 minus 3 is 1, square root of 1 is 1, 1 minus 1 is 0. Who cares about the numerator? Good, so x cannot equal 4, we know that much. Because, you know, blah, blah, blah. I'm not going to write that out. Now, what else? Is there any other issues that we need to take care of? Under the square root, right? How do we avoid negatives with the square root? What do we need to do with x minus 3? Yeah, x minus 3 greater than or equal to 0. And then we solve that, right? So that's easy to solve. X is greater than or equal to 3. Is x greater than or equal to 3 includes 4? Well, is 4 in this thing? Yeah. Yeah, everything greater than 3 includes 4. So we have to remember to remove that 4, because 4 will cause some trouble. So the domain here would be all x is such that x is greater than or equal to 3, and x is not equal to 4. So that's okay. So that's almost like cheating. You're just piling everything that you discovered, and that's okay. You don't want to have any redundancies. If this says x is greater than or equal to 5, well, who cares about 4? 4 is already not part of that. Does that make sense? So you don't want to have that type of repetition. But you can say this, or it is from 3 to 4, not including 4 union from 4 to infinity. And notice how we're completely disregarding the numerator. Who cares? Numerator is not important. Even if it reduces, even if it kills an item from the denominator, does not affect my domain. And I will come back to this point later, but if my function, let's say something like this, what is the domain of that function? All real numbers except for negative 3. I agree with that. Although this function reduces to just x minus 3, right? It's still x cannot equal to negative 3. That's still already not in the domain. Just the way this function was written, this is what we call a removable who cares what. But even if it cancels out, we have to go by the way the function was written originally. The graph of this, which we're about to start talking about graphing lines, but most of you know how to graph this, right? The mx plus b. What is the y-intercept? Negative 3, and what is the slope? 1. So I can graph this. 1, 2, 3, slope is 1. The only problem is, when it gets to negative 3 on the x, there's kind of a hole in the graph. That's what the graph of this function is. Sometimes you just have to puncture a hole in the graph. And even if it's a straight line. So the way you do that, you just add an extra term on the bottom and on the top, and that creates a hole in the graph. You're making an experiment. Everything falls along the line. Something went weird at negative 3. Just the whole lab exploded. And so this is how you convey with an algebraic model that models the output of your experiment. Everything's fine. Negative 3 things just went to hell. So that's how you put a hole in the graph. Okay? All right. Now let me give you a little break. You know, equation of the line and the slope and all that fun stuff that you all know and love, right? Well, it's on your homework and it's on the quiz. So, you know, basically equation of the line. So, how many points do I need to define a unique line? 2, right? If I give you 1 point and I tell you draw a line, well, you're going to get a different line. But if I have 2 points and I ask you to draw a line, for those 2 points, there's only one thing that can happen, right? So technically, we do need 2 points to define a unique line. But there is another way to define a line. What if I give you a point And I'll tell you, you have a line that goes through that point in southwest direction. Can you draw that line? And I mean like precisely southwest direction, not like southwestish. Where is southwest direction? That's the south, right? Is that west? Oh, that's west. So down right? So here we go. What?
Depends on which way you're looking.
Well, yeah, who cares? But you know what I'm talking about, right? If I tell you have a line that goes to the point heading that way, there's only one line that can get through that. So this is how we're going to be looking at the lines. We're going to look at them. We're going to need to have, so in order to define a line, we need to have one, any point on that line. And two, direction. Of the line. Now, there's another term that we use to describe the direction of the line that kind of tells us by how much move over, by how much move up. What is that? Slope. So, in other words, we're talking about the slope. So, let's see what you remember about the slope. We usually use letter M to represent the slope. What is that equal to? What is a slope? Just rise over run. Right. What else? Change in y. Yeah, change in y. In y over change in x. Does anybody know a fancy math symbol for change? Yeah, the capital delta, very good. So it's a delta y over delta x. Or given 2 points, it's y2 minus y1 over x2 minus x1. Right? If you actually have 2 points, that's how you compute the slope. Change in y over change in x. Very good. We have 2 equations that we mostly play with. And I'm going to go through that fast. Most of you are familiar with this. One of them is called point slope form. And that's this guy. Y minus y1 equals m times x minus x1. That's the equation of the line, where x1, y1 is just some point on the line, m is the slope, and x and y your independent and dependent variables. Right? Have any of you seen that thing? All right. Now, another equation of a line is called slope-intercept form. And that's your favorite y equals mx plus b. The way I like to do these problems, finding equations of a line, by the way, I'm covering sections 1, 3, and 1, 4 at the same time. They both talk about the same thing. The way I like to do this, first of all, gather the information that you need, which is point and the slope. Make sure you have those two. If you have those two, it'll knock out 95% of the problems. There are some weird cases with the vertical and the horizontal lines, and I'm doing it opposite. Vertical and horizontal lines. That's different. You don't need that. But for anything else, point, slope, and I like to plug it into the point slope form because you have a point and a slope. Just plug it in, simplify that, make it look like this. Okay, this is to me the easiest way of doing these problems. Some of you like just playing with this form from the beginning. It's a little strange, but whatever works for you. And I'll give you, I'll show you how to work both methods, and then you pick and choose. So here's an example. Find equation of a line. So you have a line that passes through a point 1, 2, and has a slope m equals -3. So I have all the required information. I have the point, I have a slope. I can go ahead and find the equation of a line that passes through that point and has that slope. So I'm going to do it both ways. So this is what I like. This is my favorite method. I will start with the point slope point. That's how I'm going to start this problem. I know m, I know x1, I know y1. So I can plug everything in. So this is y minus 2 equals -3 x minus 1. See what I did? I used 2 as y1, I used 1 as x1, and m as -3. And now I'm just going to simplify this. I'm going to distribute -3, and finally add 2 to both sides, so y equals -3x plus 5. Is that okay? Did I make a mistake? No? Okay. Now, by the way, what is that plus 5 thing? What is this? 5 is the y-intercept, and what is the -3? What does that mean, slope is -3? Down 3 over 1, right? So when you see an integer, always think of it over 1. So the numerator, no, it's all right. What is that? All right. Oh, okay. So the numerator is the rise, the denominator is the run. So I can actually sketch a graph of this line really fast. The y-intercept is 5, and the slope is -3, meaning what? As you guys pointed out, down 3 over 1. So down 3, 1, 2, 3, and over 1. So that's that line. Is that okay? If the slope was 3/4, how would you interpret 3/4 for a slope? Yes, up 3 over 4. Okay. Now let me show you the other way of doing this problem. So method 2. So I will start with y equals mx plus b. X and y are variables. X is an independent variable, y is a dependent variable. Right now, I only know m. M is -3. I do not know b. So right now, I know this. Right? There are 3 unknowns in this equation. X, y, and b. Now, b happened to be a constant. There's that y-intercept. And I also know that this line passes through 1, 2, meaning that 1, 2 solves this equation. If I plug in 2 for y and 1 for x, this equation has to balance. So it's still going to be an equality. So I can solve for b, right? So therefore, b equals 5, right? So that's what b is. So then the answer here, y equals -3x plus 5. So we get the same result by solving for b separately. Yeah? I like method 1 better, but I think you've seen both of them before, right? You can use either one. Any questions? How we got that? I like that one, because it's just you plug everything in and boom, the answer falls out. Okay. Let's try another one. So same thing, find equation of a line. Now line passes through -1, 4 and 3, -4. Do I have the two required pieces of information? I do not, but can I find them? Yeah. Because I have a point. I have abundance of points. I have two. But I need to find the slope. So first would be to find the slope. So m is change in y with change in x. So it's -4 minus 4 over 3 minus -1. So subtracting y, subtracting x's. Pay attention to the signs. Looks like we get -8 over 4. So the slope is -2. Right? No? Which is? Okay. So I have the slope now. I have 2 points. Which point do I use in my equation? Doesn't matter. That's right. Both of these points should work. We all should come up with the same answer. So let's use the first point. So it's y minus 4 equals m, which is -2 times x minus -1. Right? You're just plugging 1 and the x values into the equation. And then just simplify this. So y minus 4 equals -2 times x plus 1. Two negatives give me a positive. Distribute -2. And then add 4. Y equals -2x plus 2. Good? Can we do a quick sketch of this line? Let's just not even draw that. So what is the y-intercept? 2. And what do I go from there? Down to over 1 down line. Okay? Is that right? Okay. What do you know about parallel lines and their slopes? Right. Parallel lines have the same slopes. What about perpendicular lines and their slopes? Flipped? Is it reciprocal? So that's 1. Is that it? Just the reciprocal? A negative. So it's a negative reciprocal. So the key is if you multiply the slopes of perpendicular lines, you always get -1. You have a negative reciprocal. Let's write this down. So parallel lines same slopes. Perpendicular lines slopes are negative reciprocals of each other. Meaning if you have two lines, the slope of the first line is -1 over the slope of the second line, so negative reciprocal. Or every time you multiply the slopes of perpendicular lines, you end up with -1. Okay? So here's an example. Line passes through 2, 4 and perpendicular to 2x minus 3y plus 4 equals 0. Oh, we're going to have fun with this one. So, do I need all the required information? I mean, do I have all the required information? right? What am I missing? Right, I got to solve for the slope. So first I need to find the slope. Now, how would I do that? Right, I'm going to take this equation, very good. I'm going to solve for y. Because if I solve for y, that means I'm putting it into that mx plus b form so I can clearly see what the slope is. I don't care what the y-intercept is. I can actually do some selective solving. But solve for y, so we can add 3y to the other side. So 3y equals 2x plus 4, right? And then divide both sides by 3. So y equals 2/3 x plus don't care. Right? I just need the slope. I don't care what the y-intercept is, which is 4/3, but that's besides the point. So what is the slope of this line right here? Right, 2/3, right? So the slope is 2/3. It's just whatever the constant in front of x. Now, our line is perpendicular to that line. So what is the slope of our line? -3/2. Very good. So therefore, slope of our line is -3/2. Okay. So we kind of had to take a lot of steps, but you're absolutely right. First, find the slope of that reference line, and then do the negative reciprocal, and then we're good to go. So now we can finish the problem. Slope is -3/2. The point is 2, 4. So I can go y minus 4 equals -3/2 x minus 2 using the point 2, 4. And that slope. So now we can do this. Y minus 4 equals -3/2 x plus 3. When you multiply -3/2 by -2, just cancel. And finally, plus 4 on both sides. Y equals -3/2 x plus 7. Is that okay? Very familiar with this, right? Okay, this one we're going fast. We're almost done with this. Just a refresher. How many of you done with the quiz, by the way? Anyone? Finish the quiz? 1? How many of you done with homework 0? All of you should be done with homework 0. Who knows what I mean by homework 0? Okay. How about homework 2? Okay. Well, clearly, yeah. Oh, goddamn. If you are done with the quiz 1, you clearly, yeah. And then quiz by end of Sunday. Yeah, that's the due date, right? Sunday, 11:59 p.m. So you have till midnight. But think about this, Sunday midnight, probably every deadline or due dates for any assignment on my math lab worldwide happens on Sunday at midnight. So, yes, you're in a mountain time zone. So like whoever falls into mountain time zone, probably going to share the same due date as you. No, it's set for the mountain time zone. You might have to compete with students who live in, Western time zone while taking online classes that are located in the mountain time zone. Okay. Never mind, that was a little bit of, can we grab this? Can we grab this? Sure, what's the intercept? So let's say that's 7. What do I do from there? So down 3, right? 1, 2, 3, over 2, bam. Right? The slope is negative. How many attempts do you have for quiz 1? 2. Have you used both of them? Wow. Have you started homework 2? Okay. Because, remember, there are no starting dates. You can just keep going. You don't have to wait till, next week. Yeah, that's right. That's right. You show them. Were you in my class before? No, you look very familiar. Okay, so that's the graph. Were you in my class before for like 1 day? Yeah. No? Okay. Never mind. Okay, good. Now, what do you know about vertical and horizontal line? Horizontal line, what is the slope of a horizontal line? 0, because there's no rise, right? Rise is 0, run is whatever. What is the slope of a vertical line? Undefined. Because rise is whatever, but the run is 0. So division by 0 is undefined. So horizontal lines, slope equals 0. So equation of a horizontal line, that passes through some points AB is y equals b. So y is a constant. What's going on? Y is b. Y is always constant. It's flat. Okay? Or even if you think about the equation mx plus b and m equals 0, so you're just left with y equals b. Just always that intercept. So that looks nice and pretty. Now the vertical lines are a lot weirder to begin with. So the slope is undefined. Because of the division by 0. So then equation of a vertical line that passes through AB is x equals a. So x is a constant, and y is everything. Yeah. So let's do an example. Find equation of a line that passes through -1, 3 and perpendicular to x-axis. So what do you think? A line that's perpendicular to the x-axis and passes through -1, 3. But will that line be perpendicular to the x-axis? But if it's y equals 3, it's like that, right? So it's parallel to the x-axis. I want it to be perpendicular to the x. Well, you're thinking correctly. It's going to be one of the weird ones. X equals -1. Because the graph of this line, here is -1, 3, and here's the x-axis. So in order for it to be perpendicular, it has to be vertical. So yes, the equation of vertical line, x equals -1. Okay? Any questions? Very familiar stuff, right? You should be feeling very comfortable. I'm going to stop talking. I'll